All right, so I see Thelma is in the house. Thelma, if you could maybe share the link. Sorry, I sent it late. I didn't realize that I didn't schedule the today's class. Excuse me. I didn't schedule today's class on the calendar, seeing as it's an ad hoc class. But if you could share this on the, I'm told you have a WhatsApp group or something, that would be good. Hopefully people will be able to join us very, very soon. But seeing as this thing is being recorded, I guess we might as well start because I have another engagement at 8. So I'm going to start. And I will share my screen. Just wanted to reiterate what I said yesterday. Just give me a second. Give you a chance to, and this is being recorded. I know there's just, is it 9 people so far in the room, 10 including myself. Your CA will be 0. It will be turned to a 0. You know yourselves, you cheated, it's going to be turned into a 0. If you don't send that email to Lighton before end of the day, your CA will be 0 by Monday. Are there any questions? I want us to continue with lecture series number 15.
Sir.
Yes.
On the lecture slides for file systems, the file storage, where we had to do a calculation for RAM. Is it calculation for RAM or space or backups? Yes, the calculation for backups. I didn't find the calculations analysis in the slides.
Yeah, I don't remember. I can't recollect what you're talking about. Can you send me mail about that or something, and then we can look at it, send it to the mailing list or something. That's many lecture series ago. Again, I want to repeat, your CA will be turned into a 0 on Monday. And I know you will hate me, right? I'm trying to give you a chance here to redeem the 1 mark. But if you don't, you will lose all the 50 marks. All right, so something else I wanted to mention here is we're looking at the time we have left, right? Next week is the test. We're only going to do 15 quizzes. And actually, I was tempted for us to redo quiz number 15 because I know that a lot of people are cheating, right? But that's okay, right? That's okay. It's just 1 mark. And so no more quizzes. Quiz number 15 was the last one. The next assessment is going to be makeup assessment. And also very, very soon, I'm going to be sending out email with regards to those of you that qualified to sit for makeups so that we can already set up a plan for when these makeups are going to be written during the so-called study period. I don't know if study period is going to be extended anyways. And so with that being said, the makeup sessions are likely going to take place in the week after that's week after next. So week of the 9th, I believe, of November. This is when we're going to write most of the makeup assessments. If you're one of those who qualifies for a makeup and you haven't reached out to Lighton, please do let me know. Make up a plan or something. Okay, I won't bother to go through the results. You can download this or upload this to Moodle with updated slides here if you want to look at the performance. Pretty decent, although some people were cheating, right? Not everybody was cheating, but I know the vast majority of people here. Here's the thing, right? You won't be caught if you're hiring somebody else to write on your behalf. And I know there are some of you that are doing this, right? But how long is that going to last for you? Good luck with that. All right. So we got to a stage where we actually understood, right? Got a firm sense of how textual content is represented. And then also we had a thorough discussion of exactly how color gets to be represented, right? So this notion of bit depth came up. Essentially, it dictates, right? It dictates the total number of colors that you can represent, right? It turns out that there are other color modes that you tend to work with, right? So the 3 that we looked at are just some examples that I guess would help us understand exactly what it is we're talking about. But there's more here. Like for instance, you can increase the bit depth that you're working with if you want to come up with a much more clearer color, right? Same concept. The only thing here is you start compromising on things like space, for instance, right? All right. So seeing as we've set the stage for a discussion of color representation, now would be a perfect time for us to transition to talk about image representation, because it turns out that color plays a very crucial role in representing images. Right, so your typical image is represented using varying intensities of colors, really, right? And I would like to draw attention to the images on my right, two images. So there's a black and white image, ICT 1110. I don't know if you can see if that's the ICT 1110. It's deliberately, I guess, presented in that way, right? Try and put this point across here. Then right below it is your average contemporary color image or something. Not the best of resolutions, but that's fine as well, right? And it turns out that your image, right, is represented using tiny light intensities, right, which correspond to pixels. So this is usually best perceived if you try and zoom in into a typical image, right? What you will notice is that as you're zooming into the image, you start noticing that it pixelates, right? So you notice the individual pixels associated with each different image, right? And so the idea, right? The idea behind this is that each one of these individual pixels that you see is represented using a color, right? And collectively, those many pixels that you have will make up what we call an image, right? Yeah, anyway. Oops, what's happening here? There we go. Sorry about that. Right, and this zooming idea, really, I'm sure you've seen this in billboards especially, right? As you're driving closer to a billboard, you notice that you can actually see the pixels. Why? Because your average billboard will actually zoom into an image to make it appear much bigger, right? And construction work is about to start. I hope it's not starting any time soon. Right, so this is what I was talking about here. If you look at the top right image here, right, you can actually draw a grid to try and see exactly which particular pixels represent a particular portion of the image, right? So very easy for a black and white image, right? You typically have a combination of black and white colors, right? So if you look at our ICT 1110 image on the top right side there, you notice that your eye, right? Your eye is nothing more than a representation of these tiny little pixels, right? Because it's black and white, our image represents the eye, all the pixels associated with the eye ascribe the color black, right? Everything in the background is white, obviously. Same goes for the sea here. You notice that obviously you wouldn't really be able to see the sharp corners here associated with these two different pixels here, because it would be, because the pixels are much smaller, such that your eyes don't really see the difference per se, unless if you zoom into an image, right? So again, the image on the top here is represented using a bit depth of 1, right? Meaning that you can only represent 2 colors here. And then the one at the bottom here is a combination of 3 different colors, so RGB. You can assume that it is RGB, with each color intensity being represented using 8 bits, right? So perhaps the hair color for the average person in the image on the bottom here would be represented by the number 255, I believe, right? A continuous stream of 1s, right? 24 1s. If you have someone putting on like a red shirt, I suppose, as is the case with the guy at the back there, perhaps we'd assume that it's represented by a continuous stream of 8 zeros and then 0, is it 16 zeros? Yeah, 16 zeros, right? So that you have each one of these individual pixels here that are supposed to be read being represented by that color-coded combination. But the idea here is the same, right? Bit depth of 24, and then varying the values of your bits will determine the color that's going to be used to represent a particular segment or section of the image that you're interested in rendering, right? Right, so it's exactly what we're saying here. And I guess I was flipping things around here. Typically, 0 is for black, and then I believe so. Let's just check. 0 is for black, and then putatively 0 is always for black, and then 1 is for white. So if you're wanting to represent these pixels, the pixels associated with the letter I here, what we're saying is that this pixel here is going to be a continuous stream of ones and zeros, essentially. Oh, wow. That's fine. It's going to be a continuous stream of 24 ones. Right? Let's just confirm here. If I go here and say I want black, what will this result in? Right, so you notice that the color black, yeah, I don't know if you can see this part that says current, right? Current is black. If I change it to red here, you notice that current is going to be red. And you notice that just pay particular attention to the RGB here. Forget the saturation and the hue here. That's not important. But if I change it to black, what you notice is that everything, the RGB colors here are going to be all zeros. If I wish to change this to white, guess I could change this to, is there an easier way of changing this to white? I don't know what I just did. If I want to change it to white, I'll just have to, because I know I'm using 8-bit representation, I'm just changing all these values to 255. And changing them to 255 means I have a continuous stream of I don't know who has the thing, microphone on. You probably want to switch it off. It's distracting. So you notice that I have all white here, right? Why is this current here? Pay particular attention to the current, not the odd. The odd is the previous color. So the current is now white, right? And you can, by the way, you can see the change using this application software. You don't have to take it by face, it's white and whatnot. Look at the HTML notation here. It's changing. These FFs here. If I click on red, it's 2 Fs, and then this is red. I'm just going to do this, I guess. Red. If I switch it to black, it's all zeros. If I wish to switch this to, I don't know if this is purple or something, but if I wish to switch this to green, for instance, because I know how green works, I just change this to 255 here. Change the green to 255, then I will change this to 0 something. Notice that green is 00FF00, right? Yeah, anyways. So black ideally is all zeros, and then I guess now the time to just have the white or something. I don't know if anyone has white hair. Very, very soon we will, I guess. So white would be OFs one. So it would be a white here. All right. I don't know if there was a question when someone wanted to speak there, but anyway, so your image is made up of pixels, and the pixels are represented using different color intensities. The color intensities would be represented using a desired color mode, right? So is it going to be 1-bit monochrome where you just have the, excuse me, where you just have your classic black and white image. You just see black and white. At some time, the TV was black and white, right? Or are you going to want to play around with grayscale, right? Where you play around with something like 8-bit representation. The 8 bits would be used to represent the varying shades of gray, right? Where 0000 or 8 zeros would be your black, I guess. and then all ones would be like white, right? And everything in between would be different variations of gray. I don't know if GIMP has an easier way of showcasing black and white. I think there should be how to play around with different color schemes here. There should be. Yeah, but I don't want to poke around with, I don't want to start poking around with GIMP to try and figure out the different grayscale. Yeah, I suppose something similar to what you have at the bottom here or something. But Wikipedia does have this, right? So if you go to Wikipedia and just say grayscale, there's a pretty nice, and I think I showcased this to you last time. They're pretty nice images that showcase exactly how grayscale colors get to be represented. So this is what I'm talking about here, right? Why do you think you'd want to represent an image using grayscale instead of black and white, by the way? Why would you want to present an image like this?
Maybe in X-rays or something.
X-ray, black and white X-ray. Well, maybe, I suppose. Yes. No, that's true. That is true, I suppose. But the question is why? Why, right? Anyway, it is true though. X-rays are usually black and white, actually. Why would you want to do that? Okay. Maybe we should bring that question in the exam or something. All right. So this is what I was talking about. And this is the thing with most of what we're discussing, right? I don't know if that's a question. The idea that there are these simple concepts that we're introducing, but which are extremely powerful, right? So if you think about this idea of representing an image, we're saying, and if you simplify things and just consider a black and white image, we're saying your average black and white image can be represented using, I hope I have, oh wow. Your average black and white image can be represented using, there we go, can be represented using two colors, black and white, right? So you have your individual pixels in your average image being represented using either black or white or something. A very simple concept, but really powerful, right? When you consider the bigger picture, you end up with something like this, right? Something visually appealing to the eyes, something that your average person can easily recognize and interpret, right? Oh, that's an image of students writing a test in class where they are unable to cheat, right? All right. Right, same goes for your average so-called true color images, right? This is what I was talking about here, where each one of these individual pixels, like in this case, we are looking at the RGB color mode. So what we're saying is that each individual pixel that we have here, and by the way, this grid is just there for illustration purposes. I'm not saying that each one of these pixels this is how this image is represented, but it's as close as possible. It's as close as you can get to how this image is represented. So what we're saying is that each one of these individual pixels is represented using 3 different colors, right? And so the color intensity that you're interested in is dictated by varying the bits here, by varying the bits, flipping it to turn it into a 1 or a 0 or something, right? But remember, you're working with, because in this case it's 24-bit representation, you're working with numbers from, you're working with a total number of 2 to the power 24 numbers, or colors, and more importantly, you're working with colors from 0 all the way up to 2 to the power n minus 1. Yeah? Remember that? N minus 1, that formula is back here. You can't say the range of colors is from 0 to 2 to the power n, because your last number, right? Your last number, 256, cannot be represented by, I don't know if you understand this, 256 cannot be represented by By what? By 24 bits, right? Is it by 8? Sorry, by 8. It can't be represented by. It's represented by more than 8 bits. So if you convert 256, for instance, to binary, you notice that you have a total of 9 bits, which results in an overflow.
And the other reason, is it because of that reason you gave us that we start counting from 0? That's why we have to.
Well, I guess in part maybe you could say because you start counting from 0, but also because that's another way of looking at it. But also more important, if you convert the number, right? If you make a mistake of thinking that 2 to the power 24 is going to be the last color to be represented, you notice that you end up with this value here. 256 is here. But if you count the number of bits here, you have 9, right? If we are saying that our colors for a bit depth of 24 means that each color needs to be represented using 8 bits. If you have a value that goes beyond 8 bits, remember our discussion of overflow? You make a decision. Your application will either truncate this or it will tell you that there's an error or something if you're working with an application that does those things. All right. All right, so
Dr. Layton,
yes,
just there when you say that an image is made up of the pixels are made up of color, so there's a pattern recognition that is implemented in these devices. For example, if I'm wearing black and then they take a screen or a picture of me, the computer will be able to recognize that that's black and then represent it with a stream of zeros for the entire representation of that pixel.
Yeah, I mean, that's an interesting question, right? And this is where the slide comes in, actually. It turns out it's not the computer, right? This is where computer application software becomes important, because actually the thing that, once the image is captured, the thing that will show other people that this person was putting on a black tee, for instance, is the computer application software that you're using. Because the computer application software is what tells the computer to say, I want to read whatever it is stored here. I want to read it using this computer because I know it's like trying to think of a better analogy here. But for example, but anyway, so your application software is the one that does that for you. And think about this for a second. As far as I keep saying here, if you look at the image on the right here, right? That's what the computer sees, right? Assume that's what a computer sees here, although it's like just flow of electricity here. But the computer does not know, or it doesn't care whether this is an image, whether this is text. In fact, for all we know, think about this for a second. What would stop this continuous stream we have here from being text? It could be text, right? Is that not so? It could be text.
Yes.
Exactly. But the thing that tells people that are interested in consuming this data or processing this data, the thing that tells them to say this is an image is the application software that they're going to be using. And it's so putative, actually. So the person who created this image will either explicitly tell you to say this is an image or implicitly tell you that it's an image by using the extension, right? So I'll send you a file. That file will have an extension. You see a JPG, you realize, oh, this is an image. And so you know what application to use to open this image. Now, if you're a novice user and you don't know which application to use, this is where those default options come in, right? Where when you're installing an operating system for the first time, it will associate certain extensions to default applications so that you don't have to worry about making a decision of whether you should use GIMP or you should use LibreOffice. Doesn't care. If I have, here's a thing here. I have, oh, there we go. I have an image, I guess, here. It's 3.6 megabytes, 3.5. So here's the thing, right? I know a default application here is going to be, oh, it's off, I guess. Sorry, my hard drive is off here. So default application, in this case, you notice that by looking at the icon, my operating system knows that this is an image, right? So it knows that the default application that should be associated with this is, in my case, it's GwenView, right? So if you notice, if I right click and say open with GwenView is the first one there, right? Get a better image, I guess. GwenView is the default application. Wow, I thought there was a better image here or something. Yeah, well, it doesn't matter, I guess, I don't know. I'm gonna get this. So GwenView, right? But I don't necessarily have to, if I'm too dumb, right? And I decide to say I want to open this image, right? Clearly it's an image here, but I don't know that it's an image, and I decide to say I'm going to open this using, let's say, LibreOffice or something, or a text editor. I can do this, and the computer doesn't care because it's expecting explicit or implicit instructions from you, the user, on what it should do, right? So I'll go here, I'll use Kate, and I'll go to this thing here, and then I'll say I want to open this image. It will open it for me. But guess what? I'll see gibberish, right? Most of the things that I'm going to see, with the exception of meta information, because it turns out that your average image, right, is not just composed of the bits that get to represent the image to be rendered, which in this case is here. But it turns out that within this file itself is meta information embedded within there, which is why you can see this text here. It probably doesn't make a lot of sense right now, but you can see that there's some textual content here that makes a bit of sense, right? Like in this case, where you're seeing 100 GoPro, is it GoPro Hero 3 or something, Silver Edition, it's just telling you the device, right, that was used to capture the image itself. Right? Some of this content obviously doesn't make sense. Like, I don't know what this AMBA is or something. Of course, I mean, there's probably certain application, right, that you could use to try and make a little bit of sense out of what you're seeing in a binary file. Like if you consider the strings utility, which comes by default in Linux, it will probably give you a sense of what the binary file is all about. So I'll go to strings, and then I'll do more here. You notice that I get to see a little bit of, I guess, more informative information than opening using a text editor. Although still, I mean, it's just gibberish, right? Commas and weird characters, and it doesn't make sense, right? Because I've opened this using a different application, an application that is not meant to consume this type of data. This is the key here. Application software is important because it helps you consume the right type of information. All right. If you are curious and adventurous, I do encourage you to look up how people sometimes include hidden messages within images, right? I mean, it's these days, I mean, you probably find applications off the internet that can decipher secret coded messages embedded within images, but it's a technique that people sometimes use, right? So, because everything is represented using ones and zeros, so even though this represents an image, you could manipulate some of the bits here in such a way that you have like some encoded message within there or something. I guess you discussed this in 2021 or 2020 or something, computer security, I don't know, right? So computer software, very important. Again, just to illustrate this idea of the importance of bit depth here and resolution. So what we're saying is that the resolution and bit depth could pretty much be used to compute the total size or the space that this image is going to occupy on disk. Right? So given an image like this, if you are told the bit depth associated with the image, essentially how many bits are used to represent each of the individual pixels, and if you are told the width and the height, which is the resolution of the image, you can compute how much space this thing is going to occupy, right? Very easy. So we're saying that the total number of pixels is just represented by multiplying the resolution, right? So this 4640 here represents the what you might consider the horizontal width of your image, and then this is the width, this is the height. The 3480 is the height. So each image, what we're saying is that each image will normally be composed of a series of bits, right? Pixels. Sorry, it will be associated with the bit depth, and at the same time, it will be associated with, and I don't know if I can do this using Gwen view. I think I can. It also has this resolution. I don't know if you can see this. Right, so effectively, when you multiply the width and the height, you get a total number of pixels that are representing this image here. So in this case, we have 3840 multiplied by 2880. Oh, it's in binary. 3840 multiplied by 2880. Wow. 3840 multiplied by 2880. So we have 11,059,200 pixels, right? So what you're seeing here, this image here, is actually represented by approximately 11 million pixels, right? A combination of 11 million pixels are the ones that will render this image that you're seeing. Yeah, I don't know if that makes sense here. This is interesting, right? If you know that you have a total of let's use this example, a total of about 16 million pixels. And each one of those 16 million pixels is represented using 24 bits. Then you can compute the approximate file size of the image itself. Very easy, right? Because you know that a byte is equal to 8 bits, and typically the unit of measure for storage is usually a byte, right? So all you're doing here is you're saying to get the total file size for the image, you multiply the number of pixels by the formula here. You're converting. What we're doing here, by the way, if you look at this formula here, is we're just converting bits to bytes. So if we're saying 1 byte is equal to 8 bits here, then we know that we can convert them. This is supposed to be over 8 bits here. Or is it? I think let's do this the right way, right? Let's do this together. What we're saying is, if we wanted to convert, I'm just going to change this to this. If we want to convert an image which has this resolution, I want to compute the size of this image. It has this resolution, and we know that we assume that the bit depth associated with this file, usually your application software will tell you the bit depth is 24. How do we compute the size? And in fact, this would be a lot of fun if actually we use a realistic image, right? Let's use this actual image and see if we'll get something that's as close as possible to 3.5 here. So what I'm going to do is I'm just going to use this to compute this. I hope this works out. So I'll get this resolution, which is 34. And usually your device will probably take consistent resolutions. You want to look up your phone and try and see which sort of resolution it uses. And this thing is not telling me the bit depth here. I want you to see the bit depth. So what I'm going to do is I'm just going to open this using an application that I suspect is going to show me the bit depth. And what better application than GIMP, right? And I was hoping it would show me or maybe my operating system will be able to show me these things. No. That's okay, I guess. Maybe this meta information that I have on the sorry about that, on the right should be able to show me this information. Let me see. not very helpful as well. Or what we can do is we can, I hope this works. Oh, wow. We can use a utility software that could help us get more in-depth information. I hope it's XF, I think. Beautiful. So if we scroll down to this thing here, scroll up here and try and see if we can get, I'm trying to get this part where you'll be able to see the bit depth here. I hope it's there. Not quite. This is quite sad. I wonder what application I can use or we can use to check the bit depth here. That's okay. I'll look up an appropriate tool to use to try and see if we can, and then we can showcase this tomorrow or something. That's fine. It's not that. But let's assume that this image has this resolution we've checked, and let's just assume that each individual pixel is represented using a bit depth of 24. What we're saying is that we can compute the size, right? How do we compute the size? We know that total pixels is equal to this value times this value, which is just equal to this number here, right? So what we're saying is bit depth is equal to 24 bits. Another way of thinking about this is to remember that 8 bits is equal to 1 byte. Now, if 8 bits is equal to 1 byte, the question to ask yourself is, how many bytes is 24 bits, right? Your direct proportion works here. So you're just going to divide 24 by 8. You're just going to divide 24 by 8 here, so we get 3 or something. So what you're saying is that each individual pixel is going to be 1 pixel is equal to 24 bits, which is equal to 3 bytes, right? So if one pixel is equal to 1 pixel is equal to 3 bytes, and the question to ask yourself is, how many bytes is this number of pixels, right? And so you're just going to multiply 3 by the result of multiplying the resolution here, the width and the height. So what we're saying is 3840 times 2880. But it's an approximation here because I have a feeling that the color mode that is being used by that particular image is not your classic true color, which is RGB. So we're saying this multiplied by 3 to give us this number of bytes, right? So we're saying that that image should be represented by this number of bytes. Well, this number of bytes is equal to, divide by 1024, we have this number of kilobytes, yeah? This number of kilobytes divided by 1024 will give us, this is something, I'm sure it's a bit iffy here, will give us this number of megabytes. There's it's likely that the image we are looking at is represented using a different, and I think it is. It's represented using a different color mode, not your classic RGB. So if I scroll down here, yeah, you notice here color space is not your classic RGB. So which explains why it's sRGB here. But that's fine, right? It gives you an idea of how you get to that particular the value, like how much space you expect an image to occupy, right? Maybe the example we have in here might be as close as possible to this. I don't know. I don't know what color. Oh, this is beautiful. If you look at this this thing here, properties, you'll notice that I don't know if you can see this, but what you'll notice is that the color space I'm using for this example is the classic RGB. If it's a classic RGB color, what we're saying is that if we use this as an example, and I do wish we could, we had managed to derive the answer from what we're looking at, but that's fine. If this is a classic RGB color, and you have this number of pixels here, right? All you do is, we're going to plug in these numbers here. So we have 16. We use the same thing. Looking at the time, the resolution is slightly different here. This is the resolution. Because it's RGB, we know it's 24, its bit depth is 24. We can assume, safely assume it's 24. Total number of pixels is, we'll just get this number here, which is a result of multiplying the width and the height. Then we're just going to plug in the numbers here. We just plug in the numbers here. So what we're saying is that if we have this here, we are expecting that the total file size for the example we have in there is going to be 46, 40 times 34, 80, which is approximately 16 million, 16,147,200 times 3, right? So it's the total number of bytes that we have. I hope we get to the closer answer here. If these are bytes, then kilobytes is divided by 1024. Okay. Again, it's supposed to be an approximate value. Megabytes is going to be 1024, about 46. Yeah, it's still not there. I'm not sure if I may have changed a few things.
Sir.
Yes, sir.
Does the size ever go up to gigabytes?
Well, it depends on the type of device you're using. I mean, for professional photographers, for instance, those high quality images that you see, I don't know about gigabytes for an image, but certainly in the, I guess, hundreds of megabytes or something. And I think I have examples. I'm sorry that this is not working out, but this is supposed to be as close as possible you get to deriving the total size of the image, right? You still need to figure out why this is, yeah, I still need to figure out why the size is much less anyway. That's fine. But it depends on the type of image. Now, I have a few examples here where your device, by the way, can be used to, I'm going to double back initially. Your device, your average smartphone, and in fact, these digital cameras that you have here, they can be configured in such a way that you get, by default, this feature is switched off, but your modern day smartphone will allow you to take photos, to take digital, what they call digital negatives of photos, right? So these are raw images, significantly large in size. Now, if you notice this example I have here, if you pay particular attention to the sizes here, you'll notice that the sizes are different depending on the file extension that's being used. And that's because when you're changing the format of these images, you sort of like change the format and implicitly change the size as well. So observe, I mean, your average digital negative here has a size of, in this case, 32 megabytes, right? Your TIFF file has slightly larger here, but these are the file formats like PNG and G for GIF and JPEG are much smaller, right? So it is possible. It depends on the type of device that you're using, and if the device itself obviously is capable of taking taking images using different types of color modes, right? Like I mentioned, if you look up. And I hope this is there here. If you look up the different types of color modes, what you will notice is that there are certain color modes that will allow you to represent, and I was hoping I could find them here. They'll allow you to represent it. This is it here, 30, 48. If you have a color mode that is capable of representing a bit depth of, let's say, high intensity color, right? A bit depth as high as let's say 48 bits, for instance. Think about this for a second. You'd ultimately result, you'd have images that would be significantly large in size because you're no longer working with 24 bits here. It's 48, right? Which is twice the size actually, right? So, anyways.
So,
yeah.
How about you get a clear image, and then you you edit it into being black and white and gray? Does that mean that the pixelation changes and it becomes black becomes 0 and white becomes 1 all over again, or does that affect everything if you just edit it?
Yeah, I don't know what you mean by does that affect everything?
Like,
but what it affects here is it affects obviously things like the size of the image, right? Is ultimately going to be affected to a certain extent. I don't know if that's what you mean here, but
yes, that's what I mean. And the what's this? Will it for RGB? Will it still be 24 bits representing the 1 pixel, or?
well, the answer to that is I don't know the specifics, but obviously if you're using an application that is going to change, we can do this actually. An application that's going to change this to, I hope I can do this in GIMP. I hope I remember how to do this. It's ultimately going to, one of the things the application is going to do, if you're changing the color mode from true color to black and white, then one of the things you're doing is you're changing the bit depth. And in fact, changing the bit depth is what results in a reduction in the file size. So I'm just going to do a couple of things here, and I guess we'll leave it at that. I'll open this image, and then I'll save it somewhere. I don't want to mess up the original image here, so I'll save it in my I don't want to mess up this content here, so I'll dump it here. Then I will. I hope this thing will be able to show us a bit depth. Maybe not. I don't know where the properties thing came from, but anyways. Oh, there we go. Properties. This is what I wanted. Okay. So what I'm going to do is attempt to see if I can. Ah, my goodness! And I have forgotten how to mode. Oh, beautiful! It's as simple as image mode. I'm just going to change this to grayscale. Beautiful. Oh, but I wanted black and white though. And do image mode. Can't see black and white. Okay, we can use grayscale as an example. Anyways, so I'll change this to grayscale, and then I'll export this as PNG or something, right? I'll just export this as by extension. Why can I not export this? Export as PNG. I want to export this as PNG, so I'm going to go down and find PNG there. And I will call this grayscale. Oh, grayscale. And then you want to pay attention to, by extension, you want to really pay attention to these things here. In certain instances, the application won't change the extension for you, so I have to explicitly do this. If you notice, this is what I was doing with GIMP, right? If I say export this, I'm just going to export this, and then we can do a comparison of we can do a comparison between the grayscale image, and so I'm just going to open the original image also, which is here, and then just do properties here to see. But for starters, I mean, what you'll notice is that if I do this, what you'll notice is that the sizes should be, oops, the sizes were, and I think PNG is a horrible format to use. Maybe what I should have done here is still grayscale, but export it as JPEG as well. And so I'm just going to change the extension in just JPEG. JPEG, beautiful. And then I'm going to just export this so that the extension is still the same, but what we've changed effectively is just the color mode, right? So you immediately notice a couple of things here. The original file is the one that's 3.5 megabytes, right? And then the exported file, same extension, JPEG, but it's in grayscale, is 2.5 megabytes, right? What we can do is use this application software I'm using to check the properties of these different files here, and hopefully try and see if we can get some useful information associated, or better yet, we can use our trusted friend EXIF. Yeah, nothing horrible. I was so hoping I could see how have these things changed, image properties. I was so hoping I could see that. Let me just see if I can find what I'm looking for here. Come on. This is very strange. I don't know why this is not coming up. But anyways, I'll look into this. I wanted to see if we would be able to, if we could find an application that would show us the bit depth associated with these different images here. Doesn't want to show us. I'm sure there's an application. Yes, sir.
How about the normal file explorer or the image gallery you have in the operating system?
Yeah, well, I don't know what operating system you're using, but my operating system doesn't do that. Maybe Windows is able to do that, yeah. All right, so listen, I'll see you tomorrow morning, 7 hours. Good day, thank you.
Bye-bye.